Thank you very much to the Auto Twin project and to Fabiana for this invitation to talk today at this session. It's a real pleasure to tell you about what we have been doing in the field of discovery of digital twins of business processes, starting from event data using process mining techniques. I am going to start by positioning the problem, and then I'll tell you like the journey that we have taken in my research group at the University of Tartu to approach this problem in different perspectives. So the problem that we started working back in 2018, so it's been more than 5 years, is kind of very simple to formulate. I am, let's say I am a business process manager. And I manage a business process, say, for mortgage loan originations in a bank, or in an insurance company, I handle an insurance claims handling process, or closer to Auto Twin, in a manufacturing company, I handle an order to cash process, or for that matter, the manufacturing portion of an order to cash process. And every so often, of course, all the time, there are performance degradations occurring in this process, or I need to fine-tune the process, for example, to deliver better cycle times, or to deliver on lower cost, or to reduce defects. And I can see where the bottlenecks are, I can see where the sources of waste are, I can see what I can do to improve it. But before I launch a change project, that might take 3 to 6 months, might be very disruptive, and might cost us an investment, let's say, of $500,000 to automate a certain part of the process, for example. I need to kind of be sure that this is going to succeed and that I am going to get the improvements that my customers are expecting, or that the board is expecting from this type of projects. So I want to know to what extent a change of a process is going to improve it with respect to either temporal metrics or cost metrics, or productivity metrics, resource efficiency, for example, or with respect to quality metrics, particularly defect rates. And let's say the 1980s, 1990s approach to this problem, which is very, very old in the field of business process management, is to model a business process, and end-to-end of what we are doing, for example, in our customer service process, to say something, to then enhance this process, to breathe life into it by defining a number of parameters related to how much time every activity takes, how often I get a new purchase order or a new case in my process, how many resources I have in different parts of my process. And then I enter all those parameters and I run the simulation, and we get the outputs, and then maybe we fine-tune with alternative simulation scenarios. So, and this is, I remember when I started working on BPM, like if it was yesterday, it was in 2001, and one of the first consultancy projects was with a team that was modeling a large government business process for approving permits. Because they wanted to make a big re-engineering of that process as part of a replatforming effort. And it was amazing the amount of time and the amount of effort they put. I counted about 10 person months to capture one of these end-to-end processes and to do some beautiful simulation that gave some direction to the project, but then it died. 2 years later, none of the people I had worked with were left in that company, not because the project had not been successful, but because it turned out not to be repeatable. It turned out to be too much effort for anything else than some highly strategic replatforming projects that emerge every 10 years. So I was left with that. So let's see how it worked. So they started and they built a business process model. This is super simplified. And they started putting parameters, okay? Typical parameters that you will put, you go and talk to experts, talk to workers, and come up with some idea of how much time we are spending on different activities. Occasionally, you get some sample data, and you try to model it, and you find out how much time you are spending, for example, on checking your credit history or checking your application, how much time you are spending on the assessment part, how much time are you spending preparing an answer to a client, to a customer, etc. And then you start adding more details into it. You start saying, how often am I getting new cases? Say, for example, I'm getting 2 applications per hour or 5 applications per hour. During what period of time? And then you start attaching people to the tasks in the process or other types of resources to the tasks in the process. So you say, well, we have clerks and we have officers, and you start attaching cost parameters to them and calendar parameters, and you kind of start mapping the different elements or activities in your process to these different resources. And then you run a simulation with that, and then you get results, and then you start comparing with reality, calibrating your parameters until you are able to replicate how the process currently behaves, and then you start using that model to make changes. Like, for example, simulate what will happen if this part of the process in the middle gets replaced by a simplified process that is going to be implemented in a new ERP system, for example. And this kind of works. It gives you directions or where to improve your business process. It's very time consuming. These models are very difficult to maintain. But when you look into the details, it turns out they are quite inaccurate and unreliable. So apart from telling you the process is gonna improve in some way, the numbers that you get are not very reliable. Whether the improvement is gonna be 50% or 30%, the people who design these models will tell you, well, we actually don't know, because it suffices that we change some assumption and it all goes through the roof. So what is the problem? One problem is that because you are designing these process models manually, the process model is not authoritative. Yeah, you don't capture every deviation. You don't capture all the workarounds that are happening in there. Yeah. And then sorry for that, something came here. And then you then end up making a lot of assumptions that might or might not hold in reality. The second big assumption that these models are making is that the guesstimates that you did by going and talking to people are going to be close to correct. And it turns out it's often not the case. People tend to underestimate how much time they spend on a given activity. The other big assumption that these models make is that people are just performing the task that you are giving to them. They are behaving a little bit like robots. They take a task, they do it, they finish it. But that's not true. People are constantly multitasking. People are not treating their work in a first in, first out manner. They are prioritizing. They are preferring certain tasks to others. Also, traditional simulation models in the field of business process kind of group people into resource pools, we call them, and they tend to assume that everybody in this resource pool, is the same, and that is not true. So every resource, like junior claims handlers, senior claims handlers, intermediate ones, has a very different performance, and sometimes different performance on different days. Some people behave better, work better in the morning, other people work faster in the afternoon, etc. So, and biggest assumption, they assume that people are dedicated to a given business process, and that's not true. You are You might be handling purchase orders in a purchase to pay process, but that's not the only thing you do. You might also be, handling meetings related to strategic procurement. You might also be involved in some a process regarding health and safety in your organization. So you are not only doing the task that of a given process, even when you are a clerk and largely dedicated to a given to performing 2 or 3 tasks in a process. So this is the situation, say, as of 10 to 20 years ago, and therefore the end result of all this movement of business process simulation that started in the 1990s is that it failed. It did not manage to get long-term adoption. Business process simulations were at best projects that were triggered from time to time in order to address some major re-engineering questions in different organizations. So what can we do? So one of the things that started to emerge around 2010, roughly, is the idea that we can take data from the ERP or from the CRM or supply chain management or other modules of different enterprise systems, and we can extract those tables, we can combine them, and we can build what we call an event log. So a sort of tabular data source that tells you how a given process was executed case by case, so process instance by process instance, and step by step. So when did the step number 1 of the case number 1 happen? Who did it? What was the goal or the loan amount of that particular loan application, if this is a loan origination process? What was the interest rate that we offer? What was the counter offer that we made 2 days later, etc.? All of that, we assume it is recorded in a table that effectively gives you 1 row per step in a case of the process, and for every step, it tells you when it happened, what activity was performed, who did it, and any other number of parameters about that case or that step in that process. And so it goes that with that data, we can do like a lot of beautiful things. And one of the things we can do is that we can discover a process model at different levels of detail of what is happening in this process. But more than that, we can discover how much time we spend in this activity, who is doing it, what is the difference between Sue performing a given task in the morning and Sue performing a given task in the afternoon, or what is the difference in the way Sue and Bob are performing the same activity. All of that information is present somewhere in that event log, and there's a lot we can extract out of it. So the concept we started to develop in about 2018 was, let's put together all these different process mining techniques to discover process models, to discover performance metrics at different levels of details, and let's do them together to build effectively a process model learning algorithm that discovers the process in a lot of details about the performance of the activities, which we started to call at some point in time a digital process twin, because of the resemblance with the concept of digital twin. And given then a specification of a change, like for example, a user tells me what will happen if I automate tasks A and B, and thanks to this automation, we reduce the execution time of these activities, say, from an average of 30 minutes to an average of 4 minutes. So if we do that, what will be the impact on the performance metrics of the process? So we run this digital twin through a simulation engine with the change specification in hand, and then we tell you what is the performance improvement that a given change will give you in terms of end-to-end cycle time in different parts of the process, reductions in cost, etc. So if I put it as a problem, so what we do is like we take data from one or more business processes. We can take, in some cases, data from process models that we have designed on those processes, but we don't trust the process model. We use it as a reference, but then we use the data to then enhance that process model with more level of details. And given one or more performance measures that you want to improve about, for example, around cost, around cycle times, etc. Now, if you tell me that I'm going to make change X in the process, and if I can capture this change in terms of a change in the process model or in the parameters of the elements of the model, I want you to predict the values of those performance measures that you care about after you perform those interventions. So that is the big problem that we are tackling. So, and of course, we want that prediction of the performance value to be accurate on the one hand. So as little error between the prediction of the new performance that you make and the actual prediction that you will observe. And that can be captured by means of a percentage error, right? And we want that percentage error to be as small as possible, 5%, 10%, as small as we can make it. And we want also the predictions to be accompanied by some sort of reliability estimate to take into account the fact that, of course, simulation is stochastic by nature. So how did we start this journey? So we started by basically consolidating different process mining techniques into a tool suite that we call CMOD. And in version 1, CMOD, what it did is that it takes an event log, a table with the records of the step-by-step execution of different cases in a process. Typically, this event log will have 6 months of data, maybe the equivalent of a few thousands to a few 100,000 cases, for example, claim resolutions or customer service tickets. We put it through the machine that what it does is that from the data, it discovers a detailed process models with activities and decision points and parallel and branching points and so on. It then determines what are the probabilities at every decision point, what percentage of time you go left, what percentage of time you go right, etc. And then it enhances that model, which in the literature we call a stochastic process model. It then enhances it with what we call a congestion model. A congestion model is a model that tells you how people in a process handle the work that is arriving constantly, you know, in what order they are performing it, what are they prioritizing, how much time the work items are spending in the queues of the workers, etc. All of that we put into what we call a resource model that consists of resource pools with a certain capacity, timetables during which these resources work, any information about multitasking behavior, how often we get a new case, etc. All of that is in all those parameters are in a congestion model, and those two together allows us to run simulations. And one of the things we did in CMO, and that was a very good design choice in retrospect, is to not only calculate one simulation model, but to calculate several simulation models iteratively to try to find the one that is the most accurate, to improve the accuracy, to address the accuracy requirement. And then we pick the most accurate process simulation model that we found, and that's the output that we get. And that output is, you can see it as a model that allows you to ask questions about what will happen in the future if I do a change or if I do another. And that's what we call the digital process twin for what-if analysis, or DPT. So now one of the questions we have is, how do I, if I have as a digital process twin in a way. So how do I know that this digital twin is equivalent? So one of the things we do in C-mode is that we use a machine learning approach to that, which is we take the event log data and we cut it. We say there is a training set and a testing set. In fact, there are even training set, validation set, and testing set. And then we learn a digital process twin with the training set, and we test its accuracy on the testing set, which was not used to learn that model. Yeah, and the way we do that evaluation is effectively by simulating the digital twin, say 10 times. Yeah, and then we compare every time we simulate, we get a simulated log. It's like it's an event log. It's a table that tells you step by step what happened during the simulation, which tasks were performed, who performed it, etc., and we compare the output of the simulation. We compare it against the test set that we kept on hold to be able to quantify the accuracy of our model. So we do all these comparisons, and then we can calculate the mean accuracy of this model and even a confidence interval. And then there are many metrics to compare a simulated log with a real ground truth test set. The simplest one, which is the one I will be referring here today, but not the only one, is to say this is the cycle time that the simulation model predicts, and you compare it against the cycle time that you really observe in practice. And then you calculate some sort of mean error by repeating that a large number of times. So we evaluated that, and we found that the glass was half empty. So on evaluations on real-life event logs of manufacturing processes, claims handling processes, purchasing processes, and loan origination and customer service processes, so in those 5 domains, real-life data sets, we find that the error rate is high, and it's actually very erratic. And sometimes for some processes, you get error rates of up to 40%. So percentage errors of 40%, which is like, well, when you get to 50%, you start asking like, okay, by randomness, I could have done better than that. So sometimes you get appalling kind of performance or accuracy on these models. And then, but we didn't give up. We started seeing what was the problem. And one of the problems is like simulation models discovered in this way tend to hugely underestimate the waiting times in the process, the waiting times before every activity. Why? Because they are sometimes they are assuming that people are robots. If there is work and they are in that process, they will take it immediately. But people are not robots. And there are many different reasons why you need to do a task, but you don't start it now, even though you are assigned to that task as a person. So we need to take that into account. The performance was even more erratic when there was a large number of resources. It often happens, for example, in the approval phase of a purchasing process, that you have a large waiting time for some manager to approve a purchase decision. And it's not because the manager is busy approving other purchase requisitions. It's because the manager has many other things to do, does not give priority, maybe on purpose leaves this to tomorrow or Friday, right? And that creates even larger waiting times than what we can capture with these models. Also, when you have multitasking, it's amazing, but different people have different multitasking behavior, and there are psychological studies that shows that there are different personality traits with respect to multitasking. We all know the difference between males and females with multitasking, but it's even much richer than that in the psychology field. You will find very detailed classifications of different attitudes and behaviors with respect to multitasking. So multitasking is there. We have to live with that. And what was more surprising to us, that it was a very poor ability to capture the possible sequence, not the possible sequence of activities, but the frequency of the different possible sequences of activities in the process. even when using the most advanced discovery algorithms and optimizing them to death, you still have a very large error in there. So from a process mining angle, that was a little bit not expected. But so it is. And there we investigated two directions. One of them is, okay, these waiting times are nasty. So let's try to learn the distributions of waiting times, learn to predict the waiting times for each activity using deep learning models instead of trying to do it by means of like a simulation where I see which resources are available and when. So instead of making it via a simulation model, let's make it via a deep learning model. And we started a research thread in that direction, and that research thread is very active at the moment in the research community. There are several other researchers investigating how to use deep learning in the context of business process simulation. I'm not going to talk about it today. It's a nice topic from a research angle, but it's a little bit problematic in application scenarios because yes, you can try to model these waiting times and you can try to model the behavior of resources using deep learning and you can succeed in terms of the accuracy that you get. But at the end of the day, these simulations models need to be used by managers, by people, and they need to be able to change the parameters of the simulation model to capture things like, for example, what happens if I automate activities X and Y. And trying to change a deep learning model so that now it knows that this activity takes less time and it understands what are the implications of it for the other activities, it's not trivial. It's not like deep learning is by nature a black box approach, right? So, but nice research direction and it has its merits, but I'm not going to talk to it today. Today I'm going to focus on a white box approach to address these limitations. So we were faced with several sources of errors in the simulation models we were constructing from the data. And we decided to approach it in what I will call a Kaizen style. From manufacturing, you probably know Kaizen means continuous improvement effectively. So we're going to say, we're going to go after every assumption that a simulation model is making about how people behave, and we are going to try to come up with ways of modeling that, one after another. So we did not less than about 15 different iterations to try to see how we can capture, how we can improve the accuracy of simulation models by looking hard into the data and trying to identify patterns that will help us to fix that error. So I'm going to show you the main results, what worked and what didn't during this Kaizen journey of improving CMOD. So the first thing we did was to say, look, simulation models assume that there is a role called clerk or claims handler or senior claims handler for a moment. And then it says there are 10 clerks or 15 claims handlers. And it assumes that every one of them is the same. So that is what I would call pooled allocations. So there's a clerk who performs two of the activities in this process, these two, for example, and I'm going to try to look at the data of those clerks to model how fast they perform these tasks, what is the distribution of their performance, when do they work more in the mornings, more in the afternoon, etc. And then, basically, I'm going to assume that all of them are available at the same times, more or less, and that they have the same performance. So we started by relaxing that and by saying, no, we're going to try, whenever there is enough data to do so, we're going to try to model the behavior of every clerk. Every clerk has a different work schedule, different work preferences, different speed to perform a certain task. So we try to learn things for every clerk individually. We call that the simulation with differentiated resources, differentiated availability and differentiated performance. And that allowed us to get some improvements in the area of 5 to 10%. So let's say in those data sets where the error rate of the digital process twin is in the order of 40%, we brought it down to around 37%. So it's nice. it's better than nothing, but it's still too high of an error rate. But Kaizen tells you keep going, right? So another small improvement was to say, well, we know that we are not capturing very well the distribution of different activity sequences. Maybe it comes from the fact that we are modeling the decision points purely from a probabilistic angle. So we say 30% of the times I go left, 70% I'll go right. Let's try to look into the different data attributes in my data set and see if I can discover conditions when I go left versus I go right. So I, for example, I might find that when the credit score is greater than 0.5 and the loan amount is less than that, then with a 90% probability the loan will be approved. Not necessarily 100%, but with a 90% probability, so low credit score and low loan to value ratio will mean that it will be accepted, right? So that allows me to be a little bit more fine-grained in terms of how I model my decision points, but it does not give a big improvement. So it makes your model richer. It even expands the set of what-if analysis scenarios that you can do, because I can model what will happen if I start getting lower credit scores into my loan origination process. What will be the impact of that, for example, in terms of rejection rates, or what will be the impact of that in terms of cycle times or resource utilization. But the improvements, end of the day, are pretty small, and we were surprised. We were expecting more from this. Then we kept going, and this was another parallel thread, was to say, we know that we are very bad at predicting the waiting times in the process. So, for example, the waiting time between assessing the application and making the credit offer is not what we are predicting, is very far away from reality. So what we do, we try to then analyze for every activity, for every execution of activity, what was the previous execution of the activity, who did that previous activity, who did the activity, when did that resource become available. So we look hard in the data and we try to find periods, waiting times recorded in the log. So places where I see a long waiting time in the log, but it cannot be explained because the resource was not available. It's just, I don't know, the resource is procrastinating or prioritizing something else, or I don't know what. And we model that time as an extraneous waiting time. So it could be external. I don't know why that waiting time is, but I model it, and then I insert some sort of timer into the model, and then I try to discover how much time I spend in this timer, just waiting before I do the activity make ready offer. And that gave a much better improvements in accuracy. So I mean, we were already at accuracy of around 36% error rate in the worst case scenarios, and it went down to below 30%. And that was very nice finding. And in hindsight, it's very natural. So simulation models traditionally only capturing resource contention, but there are many other reasons why there are waiting times in a process. Let's just say that there are many factors, and let's just try to model those waiting times for every activity in the process and see how it goes. And then you get quite good improvements. But the biggest improvement, and then I was saying, like, in hindsight, we should have started here, is to model the availability of resources in a process, of workers in a process, probabilistically. So what that means. So traditionally, I will tell you, you will say that you are available from 8 to 12 and from 1 to 5, lunchtime in the middle, right? So if there is an activity that can be performed at 8 o'clock, well, you will go happily there and you will do it, yeah? So whenever it's green and an activity is ready, the simulation model assumes that you will start that activity, yeah? So the activity is in your in-tray, there's no reason why you shouldn't perform, you are not busy doing anything else, you are green, go for it. But that's not true. It's like we never start doing something because it's our interest. There are heaps of reasons why we might not be available to start it right away. And then what do? We say this model is, I would call it a crisp calendar model. You are on or you are off as a worker at different times of the day or of the week. What about we assume that there are distractions, when you are Friday, 4 p.m., you're already thinking about like your after hours, or Thursday, you're thinking about what's gonna go in after hours, at around lunchtime, you are getting a little bit tired, so you are less likely to start something, you don't wanna stop it in the middle, etc. So let's say that in every time slot, like in the middle, your availability, your probability of starting a task, given that the task is available and that you are available, is a percentage. So I am 30% likely to start a task if it's 8 to 9 a.m., but if it's 11 to 12, I'm 90% likely to take the task if I am available. Yeah, and if the task is there ready to be performed and assigned to me. So that we call that probabilistic calendars, and it captures a lot of phenomena, including the fact that as a worker, I might be involved in the process that we are modeling, but in other processes as well. I might be time sharing, 30% here, 30% in another process, 40% in another one. And the way this approach will capture is by saying that as far as this process is concerned, I am available with a probability of 30%, because the other 70%, I'm spending it in other processes. And that approach led to very, very substantial improvements, and up to 40% improvement in the error rate, which means that while we were somewhere around 25% error rate in the worst cases, we brought it down to under 20% error rate. Now, when you talk about an error rate in the worst cases of about 15 to 20%, so if you turn it around, that's an accuracy of 80 to 85% in the worst cases, and about 90 to 95% in the best for the simpler processes, then you have a simulation model that starts being useful. And this approach has been used not in the context of the university, but in the context of Apromore, which is my other life, to simulate business processes with 200, 300 activities, end-to-end, large mortgage origination processes, and it makes simulation models like accurate. It really makes them resemble like your digital twin. So we're getting closer to that concept. Subsequently, or along the way, we did a few other things. We tried to model multitasking, we tried to model batching, we tried to model prioritization, with then very mixed effects, which was surprising. We saw that multitasking is a big thing, and what happens is that sometimes it is. In some processes it is, in other processes in most processes it has little effect. It needs a little bit more, maybe better techniques to capture it, but that's basically where we are on this research. Now, the research has been all consolidated into a tool called CMOD. Now it's in version 5. It takes an event log, it discovers the case arrival rates, it discovers the process model, the BPMN process model, it discovers the resource individually, the assignment between resource and tasks, external delays, and all the other things I mentioned. And then it uses a technique known as hyperparameter optimization from the field of machine learning to calibrate the model, to fine-tune it automatically with respect to certain accuracy metrics. And then it returns the best simulation model, and then you can use it, and we have a bit of a UI as well, to do changes to your process or to your simulation parameters, and study what is the impact on different performance measures. You can find it, it's a command line tool at the moment, and there is a separate website that has a bit of a UI, and you can find the information at the URL that I displayed here. And with that, I'm ready to take on questions. I think that's the most exciting part of this. Please go ahead.
Thank you. I think we have a few questions in the chat. The first one from Francisco. Can you see the chat, Marlon, or we'll read it? How are the probabilities?
No, somehow no. I am in some mode that does not allow me to see the chat.
Yes, because you're in presentation mode. But if you go out of the
Maybe I will have to stop sharing in that case, right?
Okay. So the question from Francisco is, how are the probabilistic calendar defined from, one second, from data expert knowledge? What is the impact in the results if the probabilistic calendar is not correctly set?
Can you repeat the end of the question? Sorry.
Yes, I think if you open the chat, you will be able to see.
Now I can open the chat. Yes, thank you.
Okay.
I'm still struggling with the chat. I'm sorry. I found it. Yeah, I got it. How is a probabilistic calendar defined? A probabilistic calendar is defined like a regular calendar to begin with. So let me say, what is a regular calendar? It's a set of it's a union of time slots in a circadian time. So for example, you will say Monday 9 to 3, 9 a.m. to 3 p.m. and 4 to 6 p.m. and Tuesday 9 to 5 p.m. and Wednesday 9 to 12. Yeah. So and you union those time slots, and that gives you what we call a calendar. Yeah. What the probabilistic adds is that every one of these so-called time slots gets a probability. So you are available 9 to 3 p.m. on Mondays with a 40% probability, meaning that if a task is available with 40% probability, you take it. With 60% probability, you don't take it. Yeah, you postpone it to the next time slot. And of course, we can choose the time slots to be smaller or larger. We have tried making very small time slots like 50, modeling your times of the days in 15 minutes intervals or in 1 hour intervals or in like half a day's intervals. You can choose that granularity. And then we discovered that from the data, effectively using association rule mining. So we try to see like, we see that you once in the data set started a task at 9:30 a.m. But another time at 9:30 a.m. a task was available, or around 9:30 a task was available, and you didn't do it. You postponed it. And then we then from that information, from this frequency, relative frequency counts, we determined that, hey, Mondays between 9 and 10, 50% chances of the times you pick a task, 50% of the times you don't pick a task. So we discover your availability probability during the period Monday 9 to 10 a.m. And then we repeat that for 10 to 11 a.m., 11 to 12, etc., etc. So roughly that's how it goes. And then there are strategies for finding out when should I not give up. Maybe sometimes there's not enough data to calculate a probability, and different strategies for falling back. But that's roughly how it works, entirely from the data. Then users can change it, of course, those parameters if they wish, but we discovered it from the data. Yeah.
And
the impact of a calendar not being correctly set is very important. So that's what we discovered. One of the most important things is not only that the calendar is not correctly set, but that the probabilities of every time slot are not included, or that you assume that you're 100% available in every time slot. That makes your simulation model very poor in terms of predicting waiting times, particularly. Yeah. So future trends and innovation. What do you see as the most promising future development in the field of digital twins for business process management? Yeah, I think that the most promising thing, is what I would call online simulation. So traditionally, business process simulation is used for tactical decision making. So I try to see if I allocate more resources, if I get more cases per hour, if I automate an activity, if I change the order of 2 activities, by how much will my process improve? That is what we are doing, is that we are addressing a question of a tactical manager who is looking at making a change in the process as a whole. but there is a whole set of people, operational managers, who are handling claims as we speak with their teams, and who would like to know, like, hey, we are clearly overloaded right now. What are our options? Should we prioritize some types of cases? Should we call in an additional colleague from another department to supplement the existing team? Should we change the procedures that we usually use to do the credit scoring and use like more of the automated credit scoring instead of trying to manually credit score? So what is the impact of these different strategies for adapting the process on the performance of the process between now and next Tuesday? Yeah. So in the next 5 working days. And that requires you to be able to discover models that can work from an existing state. You are an existing part of your process, and on the fly you have to start a simulation of different scenarios to see where they will take you in 5 days' times with respect to the state of your work queues, the response times you give to your customers, etc. So I think short-term simulation is like a pretty important capability, and it comes with several challenges, chiefly how to make this in a very scalable manner. So how to make not only high fidelity models for online simulation, but also that you can run a lot of short-term simulations in a reliable manner in an interactive mode, because you are going to be supporting operational managers who need to make a decision like now, right? LLM integration. Yes, I think that so we are able to discover models from the data. They need to be fine-tuned. That's fine. But the problem is that these models have sometimes hundreds or even thousands of different parameters, because we are modeling every resource individually, every time slot in which a resource is available, we're modeling it individually. These simulation models have too many parameters to be edited manually by people. And I think that LLMs offer a tremendous opportunity to be able to specify your changes. What do you want to change in the process in a conversational interface, and that through an LLM, an agent is able to make the modifications in this huge simulation model to be able to then run the simulations that are required to answer your question, and then to provide you an answer in natural language, and to allow you to interact again with the conversational agent to iterate over the results that it's providing to you. Yeah. So there is an assumption. Another question about the existence of the user of the resource. Yeah. How often can we actually see resource information in the event logs? I don't think that has been a little bit of a problem. That finding the resources is not a problem. That you can always find it. Now, I agree with you that a resource can belong to many different roles. So that is why in one of the iterations we did, we said, what if we forget about the notion of role? Yeah, there is no notion of role. There are people, and people do work. Yeah, some people focus more on this task and that task. Other people focus more on that other task and the other tasks. But we are all people doing things, and that has given some improvements, particularly combined with probabilistic calendars. So we are just people who normally work at certain times of the day, but not always, and who normally do certain tasks if they are available, but not always. Yeah, and once we remove ourselves from the shackles of like resources have to be part of a role, it's amazing how much we can improve the accuracy of the simulation models. So that's a little bit the approach that we have taken in that respect. Sometimes it's a disadvantage as well, because organizationally we want to think in terms of I have roles and I have 10 clerks, right? So that's something that managers want to think about. And so there is a trade-off between accuracy here. And so, and accuracy tells you treat everybody differently, not as if they were cows, that they all look together, in roles. No, treat them as individuals. But on the other hand, indeed, from an organizational perspective, sometimes managers want to treat them as roles and want to see what happens if I increase my resource pools by half or something like that. Yeah. So one interesting challenge is like to keep the twin in sync with respect to the data. So in the face of concept drift, yeah, and to make sure that it does not invalidate the digital twin. Yeah. One of the things we have been thinking about is that we are currently assessing the accuracy of the digital twin. So as of today, how accurate, if I take the data of everything up to beginning of June, and then I try to build a digital twin from the first 5 months of the year and I apply it to the month of June, do I get good accuracy or not? But I think we should be rethinking this, and your question is very relevant in terms of like, how good is my twin at evolving with the data? Yeah. So if I look over time, over the past year, and I discover a digital twin with a data set of, let's 12 months ago, is this digital twin good at modeling how the performance of the process has been evolving throughout the years, throughout the months of the year, throughout as people have been leaving and coming back and having sick leaves and stuff like that, right? So I think we need to think in terms of accuracy, like change resistance or change resilience as being a quality dimension of a digital process twin. But neither us nor other research groups that I am aware of have started to work in that direction. I think it's really worth going there. Oh, it's Dirk. Now you're going to start doing it yourself, I guess. Yeah. Is there a limitation in the type of changes and adjustment that the manager can evaluate? Yes, certainly. So that assumption remains. There are certain parameters in these digital twins around the arrival rates, the performance of activities, and the duration of activities, etc. And you can change those parameters, but you cannot change other things. So that is a little bit tricky indeed, and I do not have a very clear idea of how to make digital process twins that could potentially allow you to model changes that effectively have not been foreseen in the design of the digital process twin. Yeah. I say I don't have an answer to that question actually. Yeah. We try not to use a black box approach. That's another question, right? There are two aspects of black box approach. There's like the aspect I want to modify it manually. And you are right, maybe nobody wants to modify the digital twins manually, and everybody's waiting to be able to do it via an LLM, for example. And maybe we're going to be able to do it via an LLM in 1 year time or 2 years time. And that's great. So I don't really need it to be black box, white box. But the black box also has like, is it possible at all to change the parameters to capture my change, right? And with an LLM in the middle and without. And I think that in the case of a deep learning models, I really suspect that end of the day, a deep learning model cannot predict on patterns that it has not seen. And this is something I have tried to study in different settings, and it's always the case. It's like deep learning models or very black box models are very good at predicting for patterns they have seen in the past, but they do not capture causal mechanisms like a simulation model does. So it wouldn't be able to predict what happens if I get twice more claims next week if I has never seen the system having twice more claims than we currently have. But I don't know, maybe I'm being too philosophical, and it will be possible to build black box models that do capture certain causal mechanisms that allow you to reason about changes. Yeah. And the last question is, I have to leave for another meeting. Thanks for this interesting webinar. And my answer is thanks to you, Fabiana and Lior, and the rest of the AutoTwin team for organizing it and for inviting me.
Thank you so much, Marlon.
Thank you. Thank you a lot.
Thank you all.
Fabiana.